Hey there, welcome to the channel. I'm João Sarubi. I've got a PhD in computer science and I teach discrete mathematics. Now tell me, have you ever heard of discrete math? Did you know that mastering it is key for anyone who wants to stand out in computing? It's involved in so many fields like computation theory, cryptography, game theory, algorithm analysis, and a lot more. Oh, and by the way, if you've ever studied logical reasoning, that topic that always shows up on exams, but people tend to ignore, just know that if you're good at discrete math, you'll crush those tests. Pro tip for anyone preparing for competitive exams. Here on the channel, I'm going to walk you through lots of logic exercises that actually pop up in real tests. So if you're into computing, math, engineering, or if you study or work in any of those fields, stick around after the intro. So, what is discrete math exactly? It's a branch of math that focuses on structures that are, discrete, separate, not like calculus, which deals with continuous things. Here, we're talking about stuff that's countable and exact. In this video, I'm going to give you a big picture overview of the main topics in discrete math. Later on, we'll go deeper. Explore the concepts, applications, and solve a bunch of practical exercises together. Trust me, it's a rich and fascinating topic. Let's kick off with propositional logic. To get that, you first need to know what a proposition is. It's just a statement that can only be either true or false. That's it. For example, 1 plus 1 equals 3. That's a proposition, but it's false. 5 times 4 equals 20. Also a proposition, and it's true. Now, if I say Professor João climbed Mount Everest, that's a proposition too. But no, it's false. I've never climbed Everest. What about this? The sum of two even numbers is an even number. You might stop and think, wait, is that true? Yep, totally true. And here's another. The sum of two odd numbers is an even number. That one messes with your head, right? But yeah, it's true. Try this. 3 plus 3 equals 6. 5 plus 5 equals 10. Both results are even. So there you go. True proposition. The Earth is in the solar system. True. The Earth is flat. That's also a proposition. But it's false. All of these are part of propositional logic, where a statement is either true or false. This is different from fuzzy logic, which deals with uncertainty and shades of truth. In propositional logic, it's black and white, true or false, yes or no. Now, not everything is a proposition, okay? If I ask, how old are you? That's a question, not a proposition. It doesn't have a true or false value. Same with commands like wash the dishes, go to sleep. Those are imperative, not propositions. And since propositions can only be true or false, we can represent them with 1 and 0. 1 for true, 0 for false. And boom, there's your binary system. That's the core of computing. That's why propositional logic is so important in discrete math and in computer science in general. Now, one classic example we study is the syllogism, like, if it rains, I'll go to the movies. It rained. Therefore, I went to the movies. If both premises are true, the conclusion has to be true. That's logic, straight from Aristotle. Then there's predicate logic. It builds on propositional logic and adds extra tools, like universal and existential quantifiers, plus deduction rules we'll dive into later. A classic example of predicate logic, also a syllogism, is all men are mortal. Socrates is a man. Therefore, Socrates is mortal. Easy, right? Another key part of discrete math is set theory. It looks at how sets relate and behave. It's huge in computer science. Sets are used in data structures, algorithms, even databases. SQL, the language used for queries, is based on relational algebra, which comes from set theory. Union, intersection, difference. All of that is set theory in action. Graph theory also lives in this space. Why? Because a graph is just a set of vertices and edges. So yeah. set theory again. You also see set theory in things like formal language theory and computation theory, like the Turing machine. That's a theoretical machine invented by Alan Turing back in 1936. He built it to explore what computers can and can't do. Why does that matter? Because Turing proved that anything a computer can do, the Turing machine can too. And anything it can't do, a computer can't either. Think computers can do everything? Nope. Some programs are just impossible to run correctly. Take the halting problem. If you give a specific program a specific input, will it finish running or keep going forever? Turing proved there's no universal program that can answer that question in every case. Fun fact, have you seen The Imitation Game from 2014 with Benedict Cumberbatch? That movie's about Turing breaking the Enigma code during World War II. There's even a rumor, kind of an urban legend, that the Apple logo with the bite taken out of it is a tribute to Turing. He died by eating a cyanide-laced apple. And by the way, there's no Nobel Prize for computing. The closest thing is the Turing Award. It's basically the Nobel of computer science. Now let's talk number theory. It deals with integers and concepts like divisibility, congruence, factorization. It's the foundation of cryptography, like RSA encryption. It also plays a role in generating random numbers, like the ones your bank token spits out every minute. Pure number theory. And then we've got mathematical proofs of theorems, statements, and propositions using discrete logic. There are different types: direct proof, proof by contradiction, proof by contraposition. For example, if it rains, I'll go to the movies. The contrapositive of that is, if I didn't go to the movies, then it didn't rain. Makes sense, right? Let me know what you think in the comments. If you're enjoying this and want to keep learning about discrete math, computing, and all these cool topics, hit that subscribe button, ring the bell, drop a like, share it with someone, and binge the rest of the content. Oh, and don't forget mathematical induction. That's another proof technique used with integers. Think of it like a row of dominoes. Knock the first one and they all fall, as long as each one knocks the next. That's induction in action. Example: ever notice the sum of the first odd numbers always gives a perfect square? 1 equals 1 squared. 1 plus 3 equals 4, which is 2 squared. 1 plus 3 plus 5 equals 9, which is 3 squared. And so on. You can prove that with induction, and I'll show you how in another video. Next up, combinatorics. That's the study of counting, arranging, choosing, stuff like permutations and combinations. Big time useful in algorithm optimization. Famous problems like the traveling salesman and the knapsack problem, that's all combinatorics. Even data compression uses this. When you want to shrink a file, you're relying on combinatorial logic. We'll explore questions like, how many 5-card poker hands can you deal from a deck of 52 cards? How many ways can you pick 4 fruits from a bowl with apples, oranges, and pears? If order doesn't matter. Then there's the pigeonhole principle. If you've got 13 people, at least 2 have the same birth month, guaranteed. We also have recursion and recurrence relations. Recurrence relations describe sequences based on previous terms, really useful when analyzing how algorithms behave. Recursion, on the other hand, is when a function calls itself to solve a smaller part of a problem. A classic example, factorial. 5 factorial, written as 5 exclamation point, means 5 times 4 factorial. And 4 factorial is 4 times 3 factorial, then 3 times 2 factorial, then 2 times 1 factorial, and finally 1. So it all breaks down to 5 times 4 times 3 times 2 times 1, which gives us 120. Pretty cool, right? Each step just peels the problem down until there's nothing left to peel. Now let's talk about graph theory. It's not about charts or bar graphs. In math, a graph is made of circles or dots and lines. The circles are called vertices, and the lines connecting them are called edges. Graph theory helps us model social networks, road systems, airline routes, the internet, even molecules in biology. And guess what? It all began with a puzzle about bridges. In 1736, a Swiss mathematician named Leonhard Euler was trying to solve a curious question. Is it possible to walk through the city of Königsberg, crossing each of its 7 bridges exactly once, without retracing your steps? To solve it, Euler created a simple diagram with dots for the land areas and lines for the bridges. And just like that, graph theory was born. Let's take a simple example. Imagine cities connected by roads. Each city becomes a vertex, and each road between them becomes an edge. With this kind of graph, we can solve problems like, what's the shortest path from one city to another? Or even, how can a delivery truck visit every city just once and return to where it started, using the shortest route possible? These are classic problems in graph theory, like the shortest path problem and the famous traveling salesman problem. Now here's another powerful use of graphs: map coloring. Let's say we want to color a map, but we want to use as few colors as possible, and no 2 neighboring regions can share the same color. That's called the graph coloring problem. Take a look at this map of Europe. Each country is a region or a vertex in our graph. Notice something cool. None of Germany's neighbors, like France, Poland, or Austria, share the same color as Germany. Now let's switch to the United States. Each state is a vertex, and edges connect states that share a border. Look at Colorado, for example. It touches several states, but none of them share the same color as Colorado. So here's the question. What's the minimum number of colors needed to color any map like this? And yes, it's one of the most surprising results in all of graph theory. That's the famous 4-color theorem. Now, just a bit of history. Even though the term discrete mathematics is fairly new, the ideas go way back. Aristotle was talking about logic in ancient Greece. Euclid, in the 3rd century BC, sits down to write the Elements. In it, he dives deep into the world of numbers, exploring integers, divisibility, factorization, and even the very essence of multiplication. Fascinating, isn't it? In India, Bhaskara was working on roots. And during the Middle Ages, Arabic scholars took things even further. In the late 19th century, Georg Cantor formalized set theory and gave us tools to work with both finite and infinite sets. So yeah, people have been studying discrete concepts for thousands of years. But it all came together as discrete math in the 20th century, once computers came on the scene and everything started running on zeros and ones. That's why anyone in computing really needs to know this stuff. That's it for today. Don't forget to like, share and subscribe. And see you in the next video.